All right, for this section, we're going to be looking at a variety of different supplemental things when talking about energy. The first section here, we're going to be talking about rotational kinetic energy and power. Now, rotational kinetic energy is still kinetic energy, but we like to categorize it separately because it's much easier to solve problems when translation or moving back and forth is separated by rotation. So here we have a chemical reaction which is releasing a certain amount of energy. We're using all of this energy to rotate a protein system, and we've been provided with the moment of inertia of this particular protein system. So our goal here is to determine the final angular speed of the protein system if it was initially stationary. And then afterwards, we're going to use our changes of energy to determine another quantity known as the power, which is the rate at which energy gains occur. In other words, it's the change in energy divided by the change in time. So it tells you how fast energy is being moved from one form to another. So to do this, again, how you do this is up to you. Just for organizational sake, I like to just make a quick little chart here because it just helps us parse our problems. So as always, what we're going to do is we're going to look at the types of energy that we have. We're going to look at how much we start with, or our initial amount. We're going to look at our final amount, and then we're going to look at the change. Now, for these types of energy, or for this particular system, we do have chemical energy. So we have energy stored in the bonds of molecules. And secondly, we have kinetic rotation. There's nothing really else here. So we're pretty much left with two. Now, with this being said, we do need to know a little bit about the math for each. Now, for chemical, this type of energy is really, really complicated if you want an explicit formula. However, luckily for us, Luckily for us, we've been told exactly how much we have. In fact, we've been told quite explicitly that chemicals, or the chemical bonds in our system, have released or lost this particular amount of energy. Given that they're losing it, we don't know how much they started with or how much they ended up with. However, this thing that we've been provided with is the change. Right, so in joules, we've been provided with the exact amount. And because it's been released, we have less chemical energy than we started with. So it should be negative. And that's basically the very first thing we're being told. Now, in terms of energy, we can actually fill in a bunch of the rest of this. But the one thing that we are going to want to know is we are going to want to know how do we quantify rotational kinetic energy. So just like with regular kinetic energy, there is a relationship for it. It looks fairly similar. Here our regular amount of rotational kinetic energy we have can be found by taking 1/2 multiplied by the moment of inertia multiplied by the angular speed squared. It's a lot similar to 1/2 mv squared because it's still a kinetic energy type, so it's no surprise that it should look pretty similar. Now, with that being said, we do know a couple things here. First of all, we were told that it was initially stationary. Doesn't really matter if it's translational or rotational. If it starts off stationary, we don't really have any initial kinetic energy in either of the types. Both of these types are still kinetic. They still require things to move. However, based on the other things we have here, we can actually fill in the rest of this chart because this chart deals solely with energies. As always, since we're not told anything else, our energy has to be conserved here. So we need the two change columns to add up to 0. And this lets me actually fill in the final kinetic energy. I didn't leave myself enough space, but it's the same number. Like so, because we need final minus initial to equal to the change. Now, once I've done this, our goal is to determine the final angular speed. So when we're looking for final angular speed, let's use a color we haven't used, let's use green. We need to know what variable it is. It's actually the omega here. Now, in our charts only deal with energies, but we need to identify the type of energy that's going to help us solve this problem. And that is the final kinetic energy. We're looking for final angular speed, so our final kinetic rotational energy will let us do this. Now, with this being said, we can use our characteristic equation to extract out whatever variable we need. So putting this in, I know that my kinetic energy in joules here, in the final configuration, I know what it is. And this has to equal to 1/2, or 0.5, times the moment of inertia, which we've been provided with. And this will be multiplied by omega squared. I'm just going to use W here in place of omega. Now, once we're here, all we have to do is rearrange and solve. So being able to do so is a skill you need to possess. Everything here is in fundamental SI units, so our angular speed will come out in hertz, or seconds to the -1. And if you've done so correctly, you should get around 44.2 hertz. And with that, we found the first thing that we've been asked to find. Now, for the second thing here, we are asked to do something a little bit different. What we're asked to do is we're asked to determine the power associated with the gain of rotational kinetic energy. Now, the gain of rotational kinetic energy, we know what it is. We know it's 2.34 times 10 to the -9 joules. Power is actually a relatively straightforward thing to calculate. If you're looking at power, what it represents is it represents the change in energy divided by the change in time over which it recurs. If you look at the middle thing, that dE by dt is the calculus notation. It means the same thing. It's still the rate of change of energy with respect to the rate of change of time. Now, in this case, we actually are just going to treat these changes as the values we've been provided with. So for here, our power is equal to our change in rotational energy, because that's the particular power that we're looking for. And this is, of course, in joules. And we're told explicitly that the time over which this change occurs is 5 seconds. Now, when you do this, it's relatively straightforward. All you're going to need to do is take 2.34 times 10 to the -9 joules divided by 5. And what you'll get is 4.68 times 10 to the -10. Now, as for the units, joules divided by seconds has its own special unit sign, which is the watt. The W there just means joules per second. If you wanted to leave it as J divided by S, that's fine as well. But keep in mind, the watts are what shows up most frequently.